distributed to a random sample of 1,500 adults in Ohio. The question asks if they support an increase in the state sales tax with the additional revenue going to education. Let P hat denote the proportion of adults in the sample who support the increase. Previous results indicate 40%. All right? So guys, when you see that 40%, you need to think right off the bat you have categorical variable. And the reason it's categorical is, hold on just a second, guys. I don't know why my daughter came in and opened up the door and left it. Hold on. Close that, huh? My daughters are here this summer. Well, they're here this summer. What do you mean they're? I mean they're not in school. It's not like I don't have them all the time. But anyway, them being able to adjust to daddy teaching during the day is kind of weird. So anyway, guys, categorical data works differently. Categorical, and the reason this is categorical is because there's a question: do you support this increase? And the answer isn't a number; it's either yes or no. So that's what makes this a categorical variable. Now, to keep you from really kind of have to think through that on every single question, instinctively you can say, when I have a percentage given in my problem, you're almost always going to have a categorical variable. So guys, as we've seen before, the mean of these problems is the percentage that you're given. And the standard deviation of these problems is the square root of the value you're given times 1 minus the value you're given divided by the square root of the sample size. Or divided by the sample size. So everything is under the square root. A lot of times students will rewrite the things I give them, and they'll try to put it like that in their calculator. I mean, if it's your desire to get all the problems wrong, then do that. Guys, this is wrong. That's never going to work. It's going to give you the wrong answer every single time. You got to put that value under the square root. So, guys, we know that 1 minus 0.4 is 0.6. So sometimes it's not as clear. So what I like to do is just go ahead in situations and just do that. So I know that 1 minus, which is usually the hardest part, so I'm just going to go ahead and have that. So I know I need 0.4 times 1 minus 0.4 divided by my sample size of 1,500. So guys, don't close that parentheses up until until everything's in there that you need affected by the square root, and the 1,500 is part of that. So guys, 0.0126 is the standard error. Now, next question is, what sample size results in a standard error of 1%? Now, I'm going to come over here and so we need our standard error to be 1%. Guys, you always got to do math with the decimal. So we need our 1% to be equal to the calculations. So we know that's 0.4 times 0.6 over some sample size. We don't know what sample size creates that. That's what we're trying to find out. Guys, I think it's clear. We're going to square both sides. Square both sides gets rid of the radical sign. So on the left-hand side, we have 0.01 squared. On the right-hand side, we have 0.4 times 0.6 over n. Now, guys, I showed y'all a trick in a previous video that says if we have a proportion equal proportion, we can flip things on the diagonals. If you haven't watched that video, you need to, because it's a nice little trick that shows up a lot in statistics. That tells me because this is in the numerator and this is in the denominator, I can switch those, making this n over 1, and I don't need to put the 1 because that's redundant, 0.4 times 0.6 over 0.01 squared. All right, so if I can put that in the calculator without doing something crazy, 0.01 squared. You guys remember these things you always round up, but it turns out that one turns out perfectly on a count. So we need a sample size of 2,400. So to get our standard deviation of the distribution of sample proportions down to 1%, we would need an extremely large sample size of 2,400. All right, if 630 of the 1,500 Ohioans were surveyed support the increase, what's the value for p hat? Well, p hat's easy. Guys, I'll tell you what, let me, my daughter needs to talk to me for a second, so let me run in here. All right, gang, sorry. All I needed was to flip an egg. So, all right, 630 out of 15. What are we doing here? 630 of the 1,500 Ohioans. What's the value for p hat? You guys remember, p hat is just found by taking the count over the whole. So the whole here is clearly 1,500 Ohioans, and the count is the number who, in this case, support the increase, which is 630. So, guys, 630 divided by 1,500 gives us a p hat of 0.42. And that can be thought of as 42%. So you can say that 42% of this sample, of the sample surveyed, or of these 1,500 Ohioans, support the increase that they're talking about here. All right, gang, what is the probability that 630 or more supports the increase? Probability starts with a P, so we know we're into normal CDF. So we want 630 or more. So I start out with 630, but remember that was taken out of 1,500 people. You can't just put the 630 there. If you do, you'll get it wrong. These problems deal with proportions, percentages, fractions. They don't deal with just a count, because 630 out of 630 is completely different than 630 out of 1,500 or 630 out of 15,000. You got to tell how many the count came from for the problem to make sense. So guys, or more goes up to E99. Our standard, our mean is 0.40. And is that right? Yeah. Mean up here we saw 0.40, and our standard deviation is 0.0126. Now, guys, you can write 0.0126 if you like. That's going to be close enough usually. I don't like to do it that way. I would rather just go ahead and type 0.40 times 0.60 divided by 1,500. In fact, I'll tell you what, let's just see if it does make a difference in the calculation. So if we go normal CDF, and put 630 out of 1500 up to E99 with our mean of 0.40 and our standard deviation of 0.0126. We get the answer of 0.05622. Let's see what would have happened if we had gone ahead and do the way that I like to do it. And I like to just go ahead and type it all out and just do the square root of 0.4 times 0.6 divided by 1500. And it's off a little bit. You know, there you go. I'll show you another thing. Well, I've seen a lot of students do. I've seen a lot of students just go ahead and type out the standard error. Because, you know, if you got a little bit of calculator anxiety, you know, all that typing that in and getting everything, if you're not a person that likes to pay attention to detail, you know, all these commas and all those divisions and all those, you know, there's a chance you might get it wrong. So what I've seen a lot of people do is they just understand that that's a weakness of theirs. Guys, we all got weaknesses. I don't care who you are. And they just go ahead and type the standard error in like that. Then what they'll do is they'll go get the normal CDF key and they'll work their problem. What was it, 0.40? Yeah. But then when it comes to that, they'll just come down and put their answer there. Because what answer does, this is a function in your calculator that will put the previous answer, the previous problem you worked on your calculator, it will bring that answer and put it right there. And a lot of students just find this a lot easier to type in their calculator without making an error than this. Now, some of you might be sitting there thinking, all right, Darby, I can do it without all that, you know, whatever. Well, if that's you, good for you. But I know from teaching this class many years that not all students are like that. So, guys, you'll see that you get exactly the same number, the same answers you got up here using that answer. So, if you get overwhelmed with all that stuff, there's a possibility for you. But anyway, guys, the answer would be 0.0569. Box it in just to make sure we know it's right. All right, scores on ACT program composite college entrance examination has normal distribution, mean 20.6, standard deviation 4.8. So at a particular North Side High School, let's see if I can get this. 36 seniors take the test. Scores at this school have the same distribution as the national scores. All right. So what are the mean and standard error of the distribution of sample mean scores for the random sample of 36 students? So, guys, this is easy, kind of a little bit redundant. So the mean is the the mean of the original population. Guys, remember, since we have a normal distribution, we don't have to worry about sample size. It's over 30 anyway, but it didn't have to be. It just had to be 2 or bigger. So 4.8 divided by the square root of 36. And yes, I do know the square root of 36 is 6. All right, so 0.8. Don't you love it when these things turn out to be like that? All right, what sample size lowers the standard error to 0.25? Right now it's 0.8, isn't it? So, but what sample size would lower to 0.25? So we need to know what n makes this 0.25. All right, well, let's just do it. We know that the standard error formula for these types of problems. Now, a lot of times students will say, well, how do you know not to use the P and the N and all that? Well, I don't have a percentage problem. I've got a mean problem. I got a quantitative problem. These are measurements. ACT scores, 22, 24, 18, 36, right? It's not yes, no, yes, no, no, yes. It's not categorical. When we give a percentage, we got categorical information. When we got means and standard deviations, we've got quantitative information. So I need this value to be 0.25. I know my standard deviation of the population is 4.8. I think that's right. Yeah. And I just need to know that. Well, guys, use my trick. Right? We've got this and this. We can switch those, making it the square root of n over 1. I'm not going to put the 1 because that's redundant. Over 0.25. Square both sides. So n is 4.8 over 0.25 squared. All right, so everything has to be squared, so I put the 4.8 divided by 0.25, so everything is squared. I always round up on these problems, so the answer would be 369. So guys, you need a sample size of 369 to lower the standard deviation of the sampling distribution from 0.8 to 0.25. What's the probability the mean score for these 16 students exceeds 22? Well, probability starts with a P, normal CDF. So exceeds 22 means we go from 22 all the way up to infinity. It's the way normal distributions work. Mean. And the standard error. All right, so the answer 0.0401. Not very likely, is it? To get a mean of 6. No, wait a minute. That says 16 students. Oops. I think that's a typo. That was supposed to be 36 students. Yeah, because it says for the 16. Yeah, so guys, that should have been n equal 36. That's a typo. First mistake I've ever made. Y'all got to see it. All right, gang, last page. Drum roll, please. All right, so just a little bit of because you're going to have these problems on your midterm. You're going to have these problems on your final exam. You're not going to have these problems on Hawks. Hawks doesn't get into these types of problems of finding a sample size to create a desired standard error. So because of that, I'm giving it extra attention here because you're going to run into these next Tuesday. Well, whenever your midterm is. So we've learned the central limit theorem as it relates to quantitative and categorical data. In each case, the standard error is different. It's defined as this when we have quantitative stuff. It's defined as this when we have categorical. What defines categorical? Guys, when you see what you're given in the problem as a percentage, you can almost be guaranteed you have a categorical problem. When you have a mean and a standard deviation given and a distribution shape, you know, normal distribution, positively skewed distribution, negatively skewed distribution, you can rest assured you've got quantitative variable. All right, so reporting, always round up. You throw out typical rounding rules. If I was rounding this to the nearest integer, it'd be 127. But when you're solving for a sample size, you throw rounding, typical rounding rules out the window, and you always round up. So 127.28 would be rounded up to 128. In fact, you can get crazy here. You could have 127.0001, which clearly is close to 127. But that would be rounded to 128. So always round up unless the value falls directly on an integer. All right. So nearly all Americans report. So what I'm doing here is I'm doing this one right here. Nearly all Americans report that they brush their teeth daily. Well, that's good news. However, only 12% of Americans report that they floss daily. Well, that's bad news. What sample size is required to create a standard error of 2.8%? First thing you got to think, guys, you can't work with that 2.8%. That 2.8% has to be as a percentage. I'm sorry, it has to be converted from a percentage to a decimal. So I have to move the decimal place 2 places to the left, giving me a 0.028. And then I have to put the standard error formula, which I know back here. I'm given a percentage, a 12%. So I know because I've got a percentage that this is what I'm going to use. So I've got 0.12. Now, guys, I know that 1 minus 0.12 is 0.88. But maybe, that's just not the talent that you were given. Well, pick up your calculator and just type it in real quick. Well, what have we done before? Have we ever seen a problem like this before? Absolutely. We squared both sides. Making. Guys, if you'll just watch these videos, you have the potential to maybe be successful in mathematics for the first time ever. I really feel that. That may sound a little cocky on my part, but the fact that you can take these things and you can slow them down and you can learn at your pace, if you'll do it. That's the whole thing. Can you get rid of Grey's Anatomy? Can you get rid of all the distractions? Twitter and Instagram, all that cool stuff. Can you get rid of that long enough to learn something? I think this is a perfect environment to do that if you're willing to make that sacrifice. All right, 0.12 times 0.88 divided by 0.028 squared. Look familiar? Yep, just what we've been doing all day. So 134 is going to round up to 135. All right, gang. I'm going to insert a trick here. There is a movie that has a famous line. Yeehaw, Jester's dead. The first 5 students who emails this to me. Now here's what you got to do to get credit. You got to email it to my Shawnee account. And remember, I do different than you. I'm at shawnee.edu. You guys are my mail, all that stuff. But faculty, professors are different. Okay. And in the subject line, just do let's just call it quiz, okay? And then just write answer, and you tell me the title of the movie. Now, guys, if you need to, just Google it. It's going to come right up. But the first 5 students are going to get 20 extra points on their homework quiz points. Does that make a difference? Yeah. This is not going to be the last time I'm going to do this. So, as we do this, as I do this more and more and more, which I intend to do, I'm going to try to have this up where I have about 5 of these. So it's going to be an extra 100 points if you're one of the one of the first 5 students that emails me the title of the movie It has a very famous line, "Yeehaw, Jester's dead." First 5, guys. If you're the 6th one, you lose out. Just like a call-in radio show, all right? You just don't, timing's everything. All right, guys. Facebook friend reports that their users have an average of 144 friends. All right, I think that's higher than that now, but whatever. If the population standard deviation is 137.73, what sample size is required to create a standard error of 8? Well, percentage doesn't apply here, so I don't have to convert anything. Numbers are just as they're presented. And I know that this is the, up here, this is the standard error formula that I need to use. So I need the standard error to be 8. The population standard deviation is 137.73. And I need to know the square root of the sample size. I need to know n that will create that. Guys, use the trick. Switch, switch. Take the square root of both sides. So let's put that in our calculator, 137.73. Divided by 8, square it all. Round up, 297. All right, gang, that's all I got. Have a good one.